Good afternoon. Today I'm going to be talking about additional models of biological systems in QuickField. Previously we looked at membrane construction using QuickField, and we could model the aspect ratio of cells and their membranes using a very high mesh gradient. And we accomplished this by making spherical cells or cylindrical cells using the insert shape with circle type of elements with slightly different radii, and we can obtain a very high mesh gradient in these regions. We also looked at complex organelles such as mitochondria, modeling the outer and inner mitochondrial membranes, and looking at the AC properties of these organelles for very high frequency and low frequencies, where we establish membrane potential across organelle membranes at very high frequencies, and low frequencies, the membrane's potential exists on the outer membrane. Today we'll be looking at electrical circuit models of biological systems, where we use electrical circuit models to simulate the response of cells and organelles, neuronal dendrites, modeling Maxwell-Wagner dispersion, the biorelaxation, skin impedance, and polarization impedance are some of the models that we'll be looking at using the electrical circuit simulator. When we're modeling fields, the current density is sum of the active and reactive current densities, where the conductivity is proportional to the active current density and the dielectric constant is proportional to the reactive current density using the AC current flow module. When we're looking at electrical circuits, we'll be dealing primarily with impedance. Using the admittance prescription, the current is proportional to a complex admittance times the voltage, where the admittance is the sum of the conductance and the susceptance, where the conductance is proportional to the conductivity and the susceptance is proportional to the dielectric constant. Inserting electrical circuits in QuickField is very simple. We're using the electrical circuit simulator. We have a tool here for inserting resistor, inductor, constant current source, capacitors, constant voltage, as well as we'll have an example coupling a finite element model block with wire connectors as well. So let's look at a circuit model, cell circuit model. This is a double-shelled cell, and we have a circuit model where the cell membrane surrounding the cytoplasm, modeled in terms of resistors and capacitors, surrounding a nuclear membrane surrounding the nucleoplasm, and this series network is in parallel with a medium resistance and capacitance. So if we go to our QuickField model, this is a two-membrane, and in order to connect a circuit to the AC magnetics or the transient magnetics, we first form a model file. Okay, it's necessary to have a model file. However, there's no connection between the model file and the circuit, but it is necessary that we have a model file when we run the simulation. Later on, we'll be connecting model blocks to the circuit, but if we want to run the circuit by itself, we need to have a model block. If we look at the circuit file, here is the resistor capacitor network. This is corresponding to the outer membrane, resistance and the capacitance, and the resistance and capacitance corresponding to the inner membrane in series in parallel with the medium and the conductance and resistance of the medium. So let's solve it, and we can now look at the coupled circuit, and we can look at the values, the current and the voltage across each separate element in the circuit simply by clicking on the circuit, or on the side panel we can look at the capacitance and the current and voltage for each one of these here. Now, what we want to do is perhaps look at the impedance of this as a function of frequency. So we can, if we go to parametric analysis with label mover, what we want to do is add values. And I'm looking at the ratio of the total current to the voltage across the supply, and we want to look at the impedance. Okay, and we record steps. We'll change the problem properties. This is frequency. I'm going to increase it in increments of 100%. If we add steps, and repeat the last step. So I'm doubling the frequency each time, starting off at 50 hertz. $12.8K, 25K, 51, almost 1 megahertz, so we'll stop at 1.6 megahertz. And we get the results. Small change at low frequencies. We can also plot the real and the imaginary components of the impedance. And if we plot the real and imaginary components of the impedance, we will obtain a Claycomb plot, which should be a semicircular shape in the complex plane. Okay, so our impedance is at least down by an order of magnitude as we're continuing to increase the frequency. Almost 1 megahertz. And we can plot the results. So you can see the impedance is decreasing with increasing frequency for our double-shelled model. Another thing we can look at would be the actual values of the resistance and capacitance, the voltages across the inner membrane as a function of frequency as well. So we could use label mover to look at these quantities. The next system I want to look at is a dendrite model, and now we're looking at the passive response of a dendrite as opposed to the active response of axon here, where you have voltage-gated channels here. So we don't have voltage-gated channels, so we're just going to have a passive electrical response of a dendrite that we can model in terms of a leaky cable model here, where we have a resistance per unit length and a membrane resistance and capacitance per unit length, and also a resistance outside of the dendrite. So let's look at the QuickField model. for the dendrite. And we'll look at the AC excitation of a dendrite. So we're applying an AC stimulation. Now, once again, there's a model file that is not associated with the circuit at this point. So we're just running the circuit simulator without an attached finite element block. And this is our dendrite model. Now, we could continue to add elements here. This is roughly 3 elements. We can continue to increase the length of this by just simply cutting and pasting. So if I wanted, say, for example, to add another network here, I will simply cut and paste and join it like this. So I can continue to build this network as long as I want to. So let's go ahead and solve this particular problem. It's an AC problem. And it's solved pretty quick. If I look at the coupled circuit, and now we can, for example, we can see the current and voltage, the AC current and voltage across any element of the circuit here, and as well we can look at the impedance of the dendrite as a function of frequency in the same way as we looked at the impedance as a function of frequency of the double shell model. One thing I want to look at, however, is a transient response of the dendrite to a pulsed field. So let's look at the transient response using transient magnetic coupling. And I'll close some of the previous models. This is our dendrite. Once again, our model file, which is not connected, and we have our dendrite. Now this time I'm applying a time-dependent voltage here instead of just an AC voltage. And this is a square wave, and I'm achieving a square wave by taking the sine SIGN of the sine SIN. And this will give us, as the sine is becoming positive, SIN becomes positive and negative, the SIGN will simply alternate between 1 and -1, and we're going to make this a microvolt excitation. So this is a transient problem. We'll go ahead and solve it. Up to 1 second. Looking at the coupled circuit. So this is the supply voltage here. You can see it's a square wave that's alternating between 1 and -1 microvolt. The current, which is slightly distorted, and across each element here we can look at the response. And we can increase the length of the chain as long as we want, as before. Dendrites are usually around 2 or 3 millimeters. They're not very long. The pulse is attenuating as it's moving along the dendrite. So they're actually very short. The next thing I want to look at is the Maxwell-Wagner dispersion, and this occurs in biological samples in AC fields where we're having what's known as a beta dispersion due to the fact that we have regions of dielectric constant, differing dielectric constants and conductivities that have interfaces that are perpendicular to an incident field here. And we can model the Maxwell-Wagner distribution with a parallel network of resistors and capacitors like this. And I'll go ahead and construct one here. Let's open QuickField. Once again, we have a model file that's not connected to AC using the AC magnetics, and I have two differing resistances and capacitances here. And we'll look at the parametric analysis with label movers. Once again, I'm going to look at the impedance for the network. And as well, I want to look at the real and the imaginary parts of the impedance too. So we'll add the real part and the imaginary part. Okay. And we'll record steps. Once again, we'll change the problem properties, frequency, increase by 100%. The solution should be a little bit faster than earlier models. This is a rather simple circuit. We'll repeat this a few times. Roughly 100 kilohertz. So we get the results. Which aren't changing very fast at low frequencies. And now I can look at the impedance. This is the magnitude of the impedance as a function of frequency, or this is also known as a Bode plot. The real part of the impedance, as well as the imaginary part of the impedance. Now, if we plot the real part of the impedance versus the imaginary part of the impedance, what we'll have is a semicircular type of plot in the complex plane, and that is a Claycomb plot. Another circuit that we can model in QuickField is a Debye relaxation circuit, and it is an RCC parallel circuit, and this has been used to model the dielectric response of suspensions of biological cells, also polymers where you have a suspension of dipole moments, and once again we can look at the Bode plot and make cocoa plots in the complex plane. Another circuit that has been proposed for a gap junction model by Fear and Stolce consists of parallel combinations of RC combinations, and these are in series with a access resistance to the gap junction. So gap junctions are connecting cells, enabling the transport of materials, and also electrically connecting cells. So this would actually be one part of a much larger network of connected cells. The skin impedance model, this is modified from Trieger's model, modeling the skin impedance and consisting of a network of RC parallel combinations, and we can simulate this in the same way as we did the previous examples. And the next one is a polarization impedance. Now, suspension of cells consisting of electrodes contacting with a solution will give rise to a polarization impedance between the electrode and the suspension. And this is giving rise to the so-called polarization effect, which is something that is very troublesome for biophysical measurements. Now, I can simulate this in QuickField. The polarization impedance model here. And we can make a Bode plot and see how this polarization is affecting. Once again, I want to look at the impedance. We'll just look at the real part of the impedance. The frequency. We'll go up to 100K. So initially the impedance of the circuit is roughly 3,500 ohms, 3,600. It's decreased by roughly an order of magnitude. So we can see that the polarization effect is causing this uprise here. And what we would really like to do is remove this polarization effect. So if we go back to our model, which I will open here, to original model, and I'm simply going to remove the polarization capacitance here. Reconnect the circuit. And we'll see how this affects the results. Once again, changing the frequency. Up to 100K. And we're going to plot the results. Okay, so you can see that the impedance is considerably reduced without the capacitive double layer at the electrodes. So this will, the low frequency contamination is in a range where the biological response is also maximum. So the biological response is going to be maximal at low frequencies, where unfortunately the polarization response is maximal as well. So we would like to have a way to remove this polarization impedance by using a remote excitation, and I'm going to show an example of how we might do that using remote excitation. We'll still have polarization impedance at the pick up the electrodes. So this is at least 3 times lower. So in the block geometry model, where I have a setup that looks like a sample cell with a remote excitation, we're using a current excitation to excite the bulk sample here, which is just given as a conducting medium, and with capacitive coupling to the end caps. Now, in this particular model, we have a geometry block that's connected to our circuit. So here we have an air region. This is the medium. It's a conductive medium. It's 1 S per M, which is roughly the conductivity of the medium. So the outer toroid, this corresponds to a circuit with tangential field of 1 amp per meter flowing perpendicular to the page here. So it would This would be the excitation of a long toroid where we have an AC electric field that's perpendicular to the plate here. Now in our circuit model, we have once again a polarization impedance because of the electrodes at the end, and also we've made a connection to the block here. So this is the current that's flowing through our finite element model is connected to this circuit, and I was able to do that inserting the insert block model here, where we can simply put in finite element components for a finite element model. Okay, let's solve the problem. Okay, so now I have a current density, and this is the AC current density in my sample, and I can look at the profile, AC current profile in the sample. So it's a pretty uniform, roughly 40 amps per square meter. In our circuit block, we have current flowing through each element in our circuit block. For example, our resistance. Another thing we can look at is the Joule heating of our solution. So let me clear a contour. And I'll simply add a contour surrounding here. And we can look at the total power flow. As well as individual locations inside of the solution region. This gives us our Joule heat.